Let's go through this build your understanding problem. A bag contains a red marble, a blue marble, and a green marble, and we're going to take one marble from the bag. So the sample space consists of the outcomes red, blue, green. What is the probability of taking the blue marble? And remember, I asked you to write down what the event is. So in this case, the event just contains the one outcome, blue, and the probability of that event, E, is n of E over n of S, which is 1/3. What is the probability of taking a yellow marble? I realize now in the examples above, I didn't write down an event E for something that wasn't in the sample space. So if you wrote down E is the set of outcomes containing only Y, I totally get why you would do that, because that seems to make sense. But that's actually not correct, because remember, an event is a set of outcomes from the sample space. And Y, yellow, is not in the sample space. So the best we could do for writing down what this event is just to say it's an empty event. In other words, there are no valid outcomes in this event. So what's the probability of that event? Well, a couple of ways you could think about it. You could say this event has 0 outcomes out of the 3 possibles, and 0 over anything is 0. Or you could just say to yourself, if something can't happen, for example, taking a yellow marble out of a bag that doesn't have any yellow marbles, you can say, well, the probability of that is 0. Okay, moving on. What is the probability of taking a marble that is not red? In that case, the event we're talking about is the event of taking either a blue or a green marble, and the probability of that event then, n of E over n of S, is 2/3. Last, what is the probability of taking a marble that is red or blue or green? So red, blue, or green. Notice that is the entire sample space. So we can either do this by saying the probability of E is n of E over n of S, which is 3 over 3, which is 1, or we can just say the probability of E is the same as the probability of S, because E and S are the same thing, and we know the probability of getting an outcome that's in the sample space is 100%, because there's no other possibilities. For build your understanding number 3, a coin is tossed twice. What's the sample space? We've seen this before, so I'm going to run through it pretty quickly. We can have heads, 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 tails, tails, heads, or tails, tails. What outcomes are in the event E, no heads? Well, that outcome is, let's see, no heads. That would only be tails, tails. So the probability of E, which is the number of outcomes in E divided by the number of outcomes in the sample space, that's 1/4. What outcomes are in the event E, exactly 1 head? That's the event containing outcomes tails, heads, heads, tails. Probability of E, as always, is n of E over n of S, which is 2/4 in this case, which reduces to 1/2. And last, the event exactly 2 heads contains only the event heads, heads. And so the probability of that event, n of E over n of S, is 1/4. Okay, now we need to talk about random variables. And what's going on here is we need to move beyond simply describing outcomes and events. In other words, by saying things like heads, 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 tails, we need to find a way to assign a numerical value to the outcomes of a probability experiment. So, for example, let's keep thinking about tossing a coin twice, and let's let x be the number of heads. So, the possible values of x are, you could have no heads, 1 heads, or 2 heads. What's the probability of each value of x? Well, we just computed that above. The probability that x is 0, meaning no heads, we computed as 1/2. The probability that you get 2, the probability that you get 1 head, in other words, that x is 1, is 1/2. And the probability that you get 2 heads, in other words, that x equals 2, is 1/4. This variable x is what's called a random variable. A random variable assigns a numerical value to each outcome of a probability experiment. By the way, notice we're using a capital letter for a random variable. And we can make a probability distribution for x using a table. So I can list the values of x. They were 0, 1, and 2. And then I can list the probability of that value of x. And those probabilities were 1/4, 1/2, and 1/4. We can also make a probability histogram. So again, the values for x are 0, 1, and 2. Let's see, our probabilities were 1/2 and 1/4. So we have a rectangle above the 0 going up to 1/2. We have a rectangle, sorry, I meant that was going up to 1/4. We have a rectangle above the 1 going up to 1/2. And we have a rectangle above the 2 going up to 1/4. Something to notice here is that now that we've switched over to this thing called a random variable, as opposed to describing outcomes, we've, in a sense, lost some information. We're no longer talking about both heads and tails. We're only talking about numbers of heads. Now, in a really simple experiment like flipping a coin, we know, for example, that if you get 2 heads, you didn't get any tails. But if it was a situation where we were drawing like red, blue, and green marbles out of a bag and our random variable only recorded the number of blues, say, we wouldn't know anything about the reds and greens because we're no longer describing outcomes in their entirety. We're simply giving a numerical value to each one. So I guess in a way that's a disadvantage because you don't have a nice intuitive description that includes all the stuff that's going on. At the same time, though, having a variable with a specific number assigned to it is powerful because it allows you to do really good analysis that you couldn't do otherwise.